All right, so someone asked me about, I guess, bgaede's theory of everything, the rope theory of everything. I've not really heard about it before. I just did a little bit of research. This video was made 6 days ago, and I think a year or two ago. Let's move this over here. There's ropehypothesis.com, and there's an archive publication. So this archive publication was from, I guess, 5 years ago. And I thought, well, why not just hear what he has to say?
I think pertains to physics, and there's the mathematical part, which is, an equation they've been looking for. And so the TOE really involves a little of both. We're going to deal with the physical part first. I'm going to talk about the physics part first. And in the second half, we'll be talking about the mathematics, how the mathematics relates to that physical part that I explained earlier, right? Okay, so let's start with the physical part, okay? Is there a way to unify, especially light with gravity, electromagnetism and gravity? Is there a way to unify, have a single theory, a single mechanism? And it's really two mechanisms out of the same entity, the same mediator. That's what it's all about, okay? And so let's start there. Let's start with what we had, and we have something like this even to these days, right? Let's put it up here. And as we have these gentlemen, okay? And they were only a few that I selected, probably the most important ones that you see up there. And what they proposed, what they came up with, was a mathematical concept, the electromagnetic wave that is still being used even to this day, okay? And what's wrong with this? Well, this is what I can say is what's wrong with it. It's a concept. It talks about two fields, and the two fields are made of vectors. Those arrows there that you see, those are vectors. And as you can see, those are all concepts. And one of the first lessons you have to learn in physics is that you need objects. You can't do physics without objects. And that's a hard lesson for people to learn. They want to do it with concepts such as field and vectors. And no, if you're going to give a physical interpretation, you're going to do the physical part of your presentation, of your dissertation, you need a physical object, okay? I mean, you can take the elephant, right? And say, look, what's the mass of the elephant? Well, it's so many tons, 5 tons, whatever, right? And you condense it into a single point. You say, well, I took the elephant and I condensed it into a little point because we're not interested in the elephant for mathematical purposes. We're interested in the mass. That's what we're going to be putting in an equation, right? The mass of the elephant. No problem whatsoever. But if you're going to move something, you're not going to move the point. You got to put the elephant back in there. You got to move the elephant. You can't move the point. Okay, and that's where people get confused because they start moving points and treating the points like physical objects when what you have is a mathematical concept, which is the center of mass. And this is more or less what's happening here with the wave. They've taken away the electromagnetic wave and they start shaking it, moving it, doing things with it. You can't do that. You got to put a physical object there, and people don't understand that. So what we've done is we replaced the wave, right? And we replaced it with the we replaced it with a rope, right? In this channel, this is what we propose. We're saying that the electromagnetic wave that these people proposed was really a rope, a pair of twine threads, a DNA-like object, right? And they confused it for a electromagnetic wave because there is a waviness to it. First of all, structural waviness to a rope, and then there's this torsion, not a transverse wave, not a longitudinal wave. It's a torsion wave. In other words, the thing twirls in situ, and you have all these goosebumps moving along, the rope. And so that's what we're saying, that the mediator of light and of gravity is that rope. Now, as far as light is concerned, I think we have some credit to our name here, okay? And that's because of this. We can explain the constancy of the velocity of light, okay, the speed of light. And you can see there that you have that little equation, little c, velocity of light, speed of light, right, equals a frequency times wavelength, okay? And the only thing imaginable that can represent that equation is a rope. There is no other structure. Okay? There is no other structure. I challenge anyone in the universe, I'll challenge even God, to come up with a thing that can imitate that can simulate that equation. And I'm telling you there ain't. Okay? There's no such other object out there. It's got to be a rope. Okay? This is it, folks. It's a rope. Okay, so you can see it has all the features of the so-called electromagnetic wave, which has been corroborated, over 100 years. It's got wavelength. We call it the link length. It's the length of a link.
So essentially, he sees this depiction and for some reason he perceives it as a electromagnetic rope. And what he's showing over here is that when you have certain boundary conditions, for example, a highly conductive surface like a mirror, then within the mirror, you only support those electromagnetic waves which have a node at each boundary, because essentially the electric your EM wave needs to be zero at the boundary, and in physics, when you study this, they do give you a single rope as an example, and this is like middle school, high school. They say attach one end of the rope, and no matter how much you wiggle it, one end of the rope will always be a node, or it will never move. And so the number of waves you can put inside is going to be limited, or the wavelength is going to be limited by your boundary conditions. But I have no idea why this double helix and where he's going with this. So an electromagnetic wave, the electric part and the magnetic part is transverse to each other. So if light is propagating towards the screen, towards you, if the electric component is going up down, the magnetic component is going left right.
It's got amplitude, right? The height, okay? And it's got frequency, because you have all these goosebumps, and the number of bumps there is the frequency. You know, if you untorque a rope, right? Let's untorque it. The links are longer, and then you have fewer links. And if you torque it more, you get more links, more frequency, and each link is shorter. And that is the equation.
So I mean, kudos to him. His brain is being creative and trying to think of, alternatives or a way to push it forward. And so, it's a good thing to do. But I can already sort of see why it's not going to work. But let's see what he has to say.
Of a rope. That's what that little C is all about. And incidentally, you know, the little C was first put in there by Maxwell in one of his books, but for the value of 300,000 kilometers per second, right? But nobody picked up on that. And there were other writers all the way through the 19th century, the beginning of the 20th century, right? And it wasn't until Einstein in about, I think, 2007 wrote a paper, and he used little C, and after that, other people began to use a little C, and that's why we use the C today as a symbol for the speed of light. Okay? Anyways, there you have it. The more you torque a rope, the shorter the links, the more links you have. That's frequency times wavelength. That's the equation of a rope. And so that's one of the things that you can say is evidence. We don't like to introduce evidence because we're not trying to convince you. We're just saying we have a right to use the rope as a mediator for light, at least for light. We'll show that it's also for gravity. Okay, so that's the first issue. The other thing that rope can explain is based on the construction of what we're going to propose here, which is how the atom is constructed, the H atom. And here you see the construction of the atom. Your two threads that make...
Well, I mean, the truth is that you're free to propose any idea you want. It only gets published in reputable journals if it's peer-reviewed, and the reviewers and the editor decide that it is worthy of publication. So, there is some bias. Of course, there's always bias. But at the end of the day, your theory is only as good as how useful it is. Unless you're doing very fundamental science. But even then, in general, fundamental science always is supported or should be supported at some fundamental level in society, because everyone believes that eventually that fundamental science is going to lead to some practical applications, either sooner or later, or even if something seems rather bizarre and out there, you never really know what's going to find an application. So
make up the rope. They also construct the atom. One thread goes through the center, constructs the proton star, dandelion as we call it, and then the other one rolls around and forms the electron shell. But you can see it's all made out of the same...
What? So he's saying you're a hydrogen atom, you got electric thread, electron shell. The magnetic thread is the electron shell. The electric thread does what?
Forms the electron shell. But you can see it's all made out of the same thread. Okay, it's one thread really in the universe, and they both construct not only the rope but the atoms. That's why the ropes interconnect every atom in the universe. So as you can see, our site is a little different than all the others. We like to think that, or everybody likes to think that they've got something different. And I think we do have something different here that you haven't heard anywhere else in the world, in any other site. Okay, and so. We're proposing a new model for the universe. We think that these people who've been doing research and theoreticians and so on, they misconceive the universe completely. They don't have the slightest idea what this universe is or how it works. Here we have a different version, and I think it works a lot better. That's my opinion, right? But you have to reach your own conclusion. Okay, so what I was saying is that if the atom is constructed by the same threads, 20 threads, as the ropes that interconnect them, then we can see why you don't add the velocity or the speed of the train to the light coming out of the train. You have your car, your headlights, and you turn the lights on. Well, if you threw a ball from your car while it's running, you would have to add the speed of the car to the speed of the ball.
That's not the case with light. Light has a different speed or a constant speed irrespective of the movement of the source. And there you can see why. If the atom is made of the same material, the same threads that make up the rope, you can see how the atom can slide along there because the threads are going over and through, right? You have the blue one going right through the center of the atom, which is what makes up the proton, and the other one goes around and forms out the electron shell. So an atom does not, while it's torquing, while it's vibrating and torquing the rope, sending light along the rope, it doesn't have to, you don't have to add the speed of the atom to the speed of light because the atom is eating into the rope, okay? So we're explaining two things, the constancy of the velocity of light, the speed of light, and also why you don't add the speed of light to the moving object, okay? The speed of light is independent of the moving object because the atom does not push light forward. That's another reason why you can't go faster than light, because you're trying to go faster than the threads that make up the atom. So, it answers all those questions at least. We have an answer for them, and again, it's up to people to ponder what I'm saying and reach their own conclusions. Everybody has his own brain, hopefully, and you don't allow yourselves to be influenced by anyone else. You reach your own conclusion. All we can do here is present the theory, okay? So that's the light part of it. Now let's look at the gravity part of it, see if we can make some sense of it. For this, I usually use this gentleman because people say, oh, who are you?
I mean, I'm not sure what this adds. It just makes things more complicated, not less complicated. You're free to send this to Sabina, and she'll pull her hair out. But it's not adding anything. I don't see what this adds. How does this help us? I mean, it doesn't help us with the equations. It doesn't help us with predictions at this point. Let me just keep listening, I guess.
We don't know who you are. I've been 29 years at this, but nobody knows me. I'm a great unknown out there, and yeah, that's life. But here's a fellow. His name is Richard Muller, and he's a professor. I think he still is a professor at Berkeley University, and he says it just like it has to be said. And you got to listen to him because he's going to tell you what the specifications for gravity have to be. Anyone who's got a theory of gravity has to exceed if possible, but meet at least what Richard Muller has to say. So listen to him. Don't listen to me. I'm a nobody. Listen to him. He's a somebody. So here, listen carefully. Here goes.
If you have the Earth with big mass here, and you have you with your little mass here, but every atom on the Earth is pulling on every atom.
What's up with the voice? Why does he sound like the Exorcist or something? He sounds possessed.
Of you. You're also pulling on it.
Yes.
You're pulling on atoms right now on the other side of the Earth.
Oh my God, this is so, it's hard to listen to.
There's a lot of atoms here. You're pulling all of them. Think about gravity. It goes right through things.
Right.
Michael's lowest prices of the season sale is going on.
Okay, so what are the two things that Richard Muller said? Well, it says that one thing is that every atom on Earth is pulling on every atom of you. Every atom of you is also pulling on every atom of Earth. Now, how do you pull if you don't have a mediator? Again, we need to do physics with physical objects. Mother Nature does not do physics with witchcraft and black magic, or what they call in mathematical physics and theoretical physics, they call it action at a distance. No such monster in our universe. Okay, Mother Nature does not work by black magic. Okay, so it's not action at a distance, it's not remote control. No, there has to be a physical object, and Muller just told you every atom pulls on every other atom. So there's got to be something between any two atoms, and we're saying it's this rope that interconnects any two atoms. Okay, so here it is again. This is his summary. Okay, just listen to him. He says every atom in the Earth is pulling on every atom of you. Okay, I think it's straightforward. You're also pulling on it. Now, what part did you?
But it's so the electromagnetic forces are much stronger than the gravitational forces at the atomic level. So essentially, like, everything on the atomic level is determined by the electromagnetic forces, whether atoms can combine into molecules or not. And then once you got billions or trillions of atoms in the form of a planet, I mean a gazillion atoms in the form of a planet, and they're held together not by gravity, they're held together by well, no, I got that wrong. Initially, the molecules are held together by chemical interactions, by electromagnetic forces that forms molecules or compounds. These interact with each other through the same electromagnetic forces to sort of clump. Once the clumps get large enough, then the combined gravity of everything starts to have an effect. but it's a very weak interaction at the lowest level. Conversely, if you look at the sun, it's, it was mostly hydrogen. It was not compounds. It was just hydrogen gas. And when you have enough of it in an area, then sure, gravity pulls it into itself. And if the mass is large enough, the gravitational pull then overcomes the electromagnetic and the nuclear forces, and then you have fusion. Okay.
You not understand. There's got to be a physical object there. Okay. Otherwise, you're doing black magic. You're saying this atom pulls on that one, but there's nothing in between them. Okay. And yeah, that's irrational.
Well, it's not really irrational. The theory, so this is why they say that there's a distinct conflict between the quantum theory and the theory of gravity or relativity, which is that in the theory of relativity, gravity is induced by curvature in the space-time continuum. So the universe itself has a continuum, and the Higgs boson, which gives your atom mass, sort of curves the continuum, which leads to a gravitational pull. And that effect is local because it doesn't happen instantaneously. Nothing happens instantaneously. Which is how they ended up measuring gravity waves and things like that. But anyway, so this is...
Okay. And then he says, the amazing thing about gravity is it goes right through things. So if you have an object in front of another object, in front of another object, gravity goes right through them. You cannot put a shield in front of you to protect yourself against gravity. There's no gravity shield. Gravity goes right through your shield. Pulls you and the shield, both of them. Okay? So keep that in mind, okay? Those two things are the things that you have to meet if you have a theory of gravity, okay? You cannot answer those two questions. You do not have a theory of gravity, period. We're done, okay? No, there's no argument on that. Okay, so we say that we use these ropes, right? Electromagnetic ropes, very thin, extremely thin, unimaginably thin ropes connecting any two atoms, and those are the ones that are going to bind any two atoms together.
Well, it's not exactly true, because this is it's the basis of the curvature in the space-time continuum is sort of the basis of, some gravitational propulsion mechanisms like the warp drive. It was just a proposal in Star Trek, but it was based on an actual idea that was related to relativity. It requires it requires a ridiculous amount of energy or mass from what we understand in our current understanding of physics, but essentially you can warp relativity to shield yourself from gravitational effects in theory.
In the universe.
So current gravitational theory, what he's saying is not really correct.
Any two atoms. Okay, that means all atoms are physically interconnected. Every atom in your body is right now connected to every atom in my body, and to every atom in my room here. Okay, that's what we're saying. Okay, I just want you to understand that is what we're saying. Okay, and here we have a little gift there that gives us an idea that of what I'm saying. You're saying that every atom of that astronaut is connected to every atom on Earth. What's happening is, as he falls, the ropes, the connecting mediators, in this case the electromagnetic ropes, they fan out. And that's the acceleration of gravity. The closer he is, it's a distance-related phenomenon. The closer he gets, the more ropes that fan out. You're talking about gazillions of atoms that form the astronaut there. Okay? So they just fan out, and that's the acceleration of gravity. Very straightforward, kid stuff, kindergarten stuff. Anybody can understand this, even a child. Okay? So physics is for kids. Physics is easy. Math is a separate issue. Math is hard. You got to go to university to learn calculus, like I did. I know I swallowed a lot of calculus, but you don't need calculus to do physics. Physics is with objects. Physics is the language of physics is illustration. If you can't illustrate your theory, you don't have a theory of physics, and you can't illustrate.
That's not exactly true. If you cannot mathematically create a model art of your physical theory, then all you're doing is essentially engaging in metaphysics or philosophy. because you have to have an intuition, a physical system in your head, or a proposal, but then you need to put it down. So I get someone who's strong in math, who can assist you, but the mathematics needs to back your physical your physical picture, and then you need to use that mathematics in order to propose an experiment, in order to be able to test your hypothesis.
Illustrate concepts. Okay? You can't illustrate. I mean, people have pride, and they do illustrate things, but then they're illustrating a concept, right? They're putting a heart for love. So the concept is love, and they represent it with a heart. Or they have a dot, and they use it to represent a point. What's a point? A location. So they use a dot for location, they use heart for love, and so on. And then they start moving the heart around, the love around, and they say, no, you got to put the heart back here. You got to put the elephant back here. Okay? You got to do it with objects. Okay, so here you have, again, you can see the different, as the astronaut gets closer to the Earth, he has a different weight for each location, okay? So maybe very, very far away from the Earth, he weighs 1 pound with respect to the Earth if we could measure him there. And the closer he gets, you can see his weight increases, okay? And maybe on Earth he weighs 200 pounds, but somewhere far away he weighs 100 pounds, 50 pounds, 25 pounds, and so on. What we're saying here is, keep this in mind, okay? Weight is location specific. Let me repeat that. Weight is location specific. Weight is a static concept, okay? Weight is not a dynamic concept. You don't need to move in order to have weight. You have weight anywhere around the Earth, what is known as a field. You have different values of the field at different locations, at different distances. So you have weight, whether you know it or not, at different locations. I don't need to measure anything for you to have weight, okay? You have weight, whether you like it or not, at any location. It is a static concept. Okay, and you say, well, how can that possibly be? Are you saying that every atom of us, is bound to every atom on Earth? Every atom of the moon is bound to every atom of Earth? Yeah, that's exactly what we're saying. In fact, I'll let another fellow, his name is...
right, but that's also what current gravitational theory, that's what we currently believe.
Brian Greene. And,
there's no need for
what
ropes.
He has to say, okay? Here goes. You'll just have to read. Okay, here goes. Okay.
Oh, these ads are really annoying. So how does gravity actually work? How does the Earth pull on the moon across hundreds of thousands of miles of empty space? They behave as if they're connected by some kind of invisible rope, but everyone knew that wasn't true.
Yes, we're connected by not one rope, but invisible ropes, and they got rid of that notion. Why? Because they said, well, I can't touch any ropes at anything there, so there's nothing there. It's action at a distance. And what they didn't realize, you have to do physics using things. You can't do physics without things, and they're doing it without things. Or worse, they're putting a concept in there, such as field, energy, mass, and they're going to be doing physical interpretations with mathematical concepts. That's what the problem is. No, there is a rope. Not one rope, like Brian Greene said there. There are many ropes, gazillions of them. For every atom of the moon, there's a rope connecting it to every atom on Earth. So the Earth swings the moon around like this. Just as simple as that. I think any child can understand what I'm saying here, okay? It's just like that. That's what gravity is. Gravity has to have a mediator, okay? And it's got to be an elongated, very thin mediator that connects any two atoms in the universe. Straightforward. That's what we propose here, okay? And yes, there's a unification also between light and gravity, that they both have these features, and this is how they represent them. It's the inverse square law, okay? The farther away you go, the light becomes dimmer, it's less bright, right? And the farther you go, gravity becomes weaker, okay? So it's like they have, light and gravity seem to have very similar features, okay? And so what do? Well, we say that with the ropes you can explain that. Here you have them. The closer you are to, in this case, a screen, right? The more the ropes fan out, okay? And not only do you have a brighter screen, but also if, like when you approach the Earth, the closer you get, the ropes fan out, and now you have more gravity. You have a greater acceleration, okay? But keep in mind, weight, which is what Newton's equation really measures, right? The closer you get, the stronger gravity is, but it's that force, they say. They use it as a force. The equation is a force equation, but there is no force because any location, without any force intervening, okay? Any location, like if we took a snapshot of the universe, God's camera, took a snapshot, there would be no motion. You would have weight at that location. And you say, but I haven't moved. I haven't pressed down on the scale. You don't need to measure anything. You have weight anywhere around the Earth, okay? Very non-debatable, okay? Okay, and so some people say, well, why can't we touch these roads? Why can't,
So a couple of things. One is, yes, it's been a while, but weight essentially is the effect of your mass on the gravitational pull of the Earth, which is about 9.8 meters per second is the acceleration that you're experiencing towards the Earth. And so that's why when you leave the lower Earth orbit, you experience weightlessness because you don't experience weight. Your mass is the same, you've got the same atoms, so you have the same amount of mass, but the weight that we measure is the force that our body exerts on the ground or on the weighing scale. So this is not anything new, this is very old. Also, back in the day, in the time of Newton, scientists thought that the universe had this substance called ether through which light propagated. And you can look it up, but they actually, again, use mathematics to demonstrate that if ether existed versus if there was no ether, you could experimentally test and measure if there was ether versus if there's vacuum. And much to everyone's surprise, much to the physics community's surprise, when they performed the experiment, they found that there was no ether. And so what he's saying is not exactly correct. So it's, he knows some of the story, but not the whole story.
If they're there, right? And people say, not only touch them.
I mean, if you want, so ether experiment, the Michelson-Morley experiment. The Michelson-Morley experiment was an attempt to detect the velocity of the Earth with respect to the hypothetical luminiferous ether, a medium in space proposed to carry light waves. No such velocity was detected, and this result seriously discredited ether theories. The experiment was conducted by an American physicist, Albert Michelson, using an interferometer, right? So the theory is that if there is an ether, you're going to experience, I guess, redshift or something of that sort. So yeah, see, you can read through this, but this is the experiment that demonstrates that there is no ether.
Because if you can't touch them, we pass our hands through them. In fact, I'll prove this to you. This is an experiment that you probably want to do at home, always in the presence of a relativist, right? And here we have, this little straw here in the center, and I'm going to drop it, okay? And if you drop it, it always falls downwards. This is what you'll verify, okay? Now, this is the trick, okay? Maybe you can get another person to help you out, okay? What you do, you have this, right? This is a straw, by the way, so it's kind of thin, okay, and very light. And I'm going to let go of it, okay? And it comes down, right? Now, what you can do, and I'm going to do it here now, very dangerous thing is, I'm going to pass my hand, and you can see that all the ropes that are connecting this straw to every atom on Earth, and I'm passing my hand right through it. So you're saying there's nothing there, because I can't see it, and I can't touch anything here. So, if we're going to do it like Mr. Muller said, and every atom of the straw is connected to every atom on Earth, and there's got to be a connector, I'm passing my hand right through all those gazillions of connectors, okay? So we either do black magic and say action at a distance, remote control, witchcraft, whatever you want to call it, or we do physics, saying there is something connecting every atom of this device to every atom on Earth, and I'm passing my hand right through it. Okay? So you can let it drop, and hopefully you could measure the speed, in other words, the acceleration, which should be 9.86 meters per second square, right? That would be the acceleration of whatever object you drop on Earth, barring, air friction. But if you drop an elephant, there's very little friction there. You drop a stone, they should pretty much fall at the same time. And if you pass your hand while they're falling, okay, so you pass your hand.
So action at a distance, I believe, is a concept in physics that an object's motion can be affected by another object without the two being in physical contact.
Right through there while they're falling, you'll see that your hand does not affect the acceleration. In fact, you can probably do it with a parachutist. The parachute guy goes slowly, and he's falling on Earth because gravity is pulling on him, right? In other words, he's falling and accelerating due to all these ropes fanning out. And you can pass your hand below the parachutist, and he'll fall at the same rate. Your hand will not affect anything, okay? So, yeah, that's the issue. And people say, well, Bill, you're crazy. You're saying that ropes not only are invisible and intangible, but they go right through each other. Yeah, not only the rope, my hand goes right through them as well. And so how can that be? That's irrational. That's unthinkable. And so, there was a series in the 60s I used to watch a lot. It was known as the Untouchables. Okay? They were untouchable. Couldn't touch them. Okay? And quantum mechanics also has come up with a whole bunch of untouchables. And nobody questions it. See, here's some examples. Let me read them out to you here. When space.com, around 65 billion neutrinos manage to stream through every square inch of your body every single second with no discernible effect. They go right through you. Through every atom, through every thing that builds your body. Neutrino typically pass through normal matter, unimpeded, undetected.
Okay.
And nobody questions this? I mean, when I say the rope goes right through the rope, you say, no, Bill, you're crazy. How can a rope go through a rope? But here, the neutrinos go through everything, untouched. They go right through things, and nobody questions that. Nobody says, hey, how can that possibly be? How can neutrinos go through things and not touch them? You have a little ball going through another ball, right? And they go right through it. Nobody questions that. Photon.
Well, I mean, light goes through a window. It goes through glass. It's the same thing. It's just not absorbed. your physical body is transparent to a neutrino, the same way that glass is transparent to, or transparent glass is transparent to photons in the visible spectrum.
Photons cannot couple directly to each other in a fermionic field according to Landau-Yang theorem.
Right.
So photons also go through things. How about gravitons? They exist then like photons, and unlike gluon, gravitons do not interact with other particles of their kind. They always say they're weakly interacting particles. They interact weakly with matter. They use that fancy wording. What they're saying is it goes right through it. That's what they're saying. And so you say, well, how can that possibly be? And nobody questions that. See, this is the problem. The problem is that everybody questions when I use the rope. And they say, well, how come nobody questions the particles that these people talk about? Now,
The reason why is because all of those statements are based on physical theories that have a mathematical foundational model, and using the mathematical model, they were able to design experiments with predictions, and those experiments confirmed that the mathematical model was correct well within the error bars. So that's why the physics community accepts these things. When we say there's a paradigm shift, it doesn't mean that everything else is wrong. It just means that everything is right within our known boundary conditions or our limits, but when we open up the limits, there's another world of physics that exists that also supports what we currently know. So, for example, relativistic. So Einstein's theory of relativity did not prove that all of Newtonian mechanics was incorrect. Newtonian mechanics had been shown to be extremely accurate within certain boundaries, but then when you extended those boundaries, there were these flaws or inconsistencies in measurements. But once you used relativity, then at those extreme conditions, relativity predicted what was seen out in the universe, in the cosmos. And if you take relativity and set the boundary condition of what we experience on Earth, then you naturally get the mathematics of relativity reduces to the mathematics of Newtonian mechanics. So that's why math is very important. So physics is a very difficult discipline because it requires a number of different aspects, of which math is a very important aspect. And so if you don't follow the math, if you don't use the math, and you don't respect the math, then I can see why you would end up very confused. Like this.
now there's a caveat there, a tiny caveat you have to keep in mind, okay? Particles can only push. Okay? Particles go one way, okay? A rope or anything that's pulling, right, goes in two directions, okay? And so when people say, well, hold it, you're saying you're pulling something cuts right across it and doesn't cut it? And so that's where people start asking the question. But really, it's no different with particles. If you take two hoses full of water and just let the water run on both hoses, you put one against the other, the water will bounce. So if particles go through each other, not a single one should bounce out. So in that sense, there's no difference between push and pull. But people start questioning the pull because they say, oh, it cuts across the rope, but it doesn't cut in and continues pulling. Yeah, it's like a river going through another river. It doesn't maybe stop the other river from flowing. Think of it like that. But yeah, that's Mother Nature's universe. So two lessons you got to draw from what we've never made assumptions before is one, that you need objects to do physics, and the other one is that the objects Mother Nature uses can cut across each other. Not only are they invisible and tangible for our regular everyday macro world, they go right through each other. And until you come to terms with that, until you realize that, you're never going to understand what is out there in our universe or how it works. So those are two things you need to understand. You need physical objects to do physics. You can't do physics with concepts, okay? And the objects Mother Nature uses, the ones she uses as mediators, they go right through each other. Until you come to terms with that, you realize that, you won't understand how this universe works. And here what you have, here's an example of another thing that goes right through each other. Nobody questions it at all. Here you have Arvin Ash, talks a lot about, has a show on physics, right? And what he does, he talks about fields. I want you to listen to him because he's telling you all the fields that we have out there. Now listen carefully to what he has to say, all the fields that are out there. Okay, here goes. Listen.
All these fields extend out in all of space-time. In other words, the
Oh my god, why does he do this? It's so disturbing.
fields are always there and exist everywhere, including inside your body.
Right?
Now, although they exist everywhere and you can't see them,
They are not nothing. They are teeming with virtual particles. These are particle-antiparticle pairs that get created and destroyed. They come in and out of existence constantly. These virtual particles can't be measured, but nature allows the creation of these virtual particles by letting them borrow energy from the vacuum.
Okay, yeah. So this all has a rigorous mathematical foundation.
Okay? So what is he saying? He's saying there's all these fields. The vibration of these fields creates these particles, right? They're not discrete particles, they're peninsulas, not islands, because they stick out of the field. Okay? Great, let's not worry about that. But there are many fields. There's a field for every particle out there, and they stretch forever. Well, don't these fields that make up particles, right? Don't they go through each other? Nobody asked that question. We have all these fields that are going through each other. We have all these waves coming out of two black holes that are merging. All these waves travel where? Along space-time, hopefully, right? And we have all these waves from all the black holes in the universe, and they don't collide, they don't interfere with each other. How can you measure anything out there if you have gazillions of black holes, and not to mention other galactic components, sending waves everywhere? You know, the universe should be a mess. And they claim that they measured waves coming from the collision of two black holes. You know, there's something wrong with that, right there and then, okay? But yeah, so here we have, again, the synthesis of what good old Arvin Ash said. You know, all these fields extend out in all those space-time.
So, I mean, it is a little bit frustrating because essentially it sort of feels, as a physicist, it feels really frustrating because he's skipped all of the steps on the foundations of physics to explain how we ended up believing there were fields. Like the whole conversation about the particle nature of atoms versus the wave nature of atoms. I mean, there are deep discussions and experiments and models. There was a lot of peer reviews, a lot of competition with a lot of ideas. And the reason why we have the physics that we have today is because it was experimentally demonstrated that this is the physics that plays out. And so it's a bit frustrating because looking for a paradigm shift does not mean that we say that all of our current physics is garbage. That's not it at all. What it does mean is that you find these edge cases which are not explained by our current physics, and you look for a deeper theory that explains not only those edge cases, but whose mathematics, when taken into the realm, when reduced to our current contemporary physics, reduces to the laws that we know in contemporary physics. So the rope theory is all well and good, but it needs to have some sort of mathematical foundation in order to, because this is right now half a theory. It's not even a theory. It's not a proposal at all. It's not a thesis. It's just half an idea of everything is made out of ropes. Cool. Can you find someone to work with to figure out what the equations look like? If the equations look exactly like what the current wave equation is, then that's great. But what else does this give us? What other math are you able to propose? And then use that math in order to try to figure out an experiment to demonstrate that everything is a rope. So this essentially is the reason why I mentioned Sabine Hossenfelder, because this is sort of like, I don't know, the layman string theory, where essentially in string theory they say everything is made out of strings. So it's kind of similar to what he's saying, except they say at the very smallest, most fundamental level, everything is strings, and it vibrates in 7 dimensions, 11 dimensions. And the reasons why we only experience 3 + 1 dimensions is because the other dimensions are so small that they wind inside each other, or we don't, even though they're so small, we don't experience them. And, so, but they actually have very rigorous math in which they try to demonstrate that their string theory reduces to our current, contemporary applied physics. But it's a frustrating field for many people because while it feels like resources are taken away from the applied sciences in the West, the truth is that resources are being taken away from everyone, because the economy is kind of shifting over to another country, it appears, or another block. And so Sabine gets really frustrated at people who essentially are paid to muck around with ideas and math that is not experimentally testable. So this is like layman's string theory because it's kind of similar. There's nothing I can test. There's nothing I can do. It's just your idea. That's great. It's not helpful.
The fields are always there. And
I mean, that's not exactly true. It's helpful because, in this great social consciousness, this is how creativity works. Is you're just coming up with ideas. Boom, boom, boom. You try to put down ideas. And as someone very wise once said, like, you're a very successful creative person if every 1 out of 10 ideas is actually correct. What that means is that even for the best of people, even for top scientists, 9 out of 10 of the ideas are wrong. But they have the rigor to work through the ideas and figure out which of their crazy ideas could work and which of their crazy ideas are just not at all correct. So from that aspect, it's good having stuff like this and thinking about it, but I don't really see how ropes helps us at all.
exist everywhere. Fields, right? So they're all superimposed fields. They create these particles, right? And he's saying they're not nothing, they're something, okay? Something means that, you have a ball or whatever a particle is, and all these vibrating fields, they're superimposed, I guess. Well, how can they go through each other? Why doesn't anybody question the fact that all these fields, energies, waves, what else? They don't go through each other? Nobody questions this, neutrinos, so on. So this is the issue. The issue is, before you come and say, look, how do you, what?
I mean, we did question it, so the entire sciences questioned all of this, but experimentally, again and again, it was demonstrated that they do go through each other, and using the current math and physical theories, it works. So, the sciences are in some level a very practical discipline. If it works, it works. You just accept it and move on. But you got to propose something. So I don't understand what is being proposed here.
You're crazy, Bill. How can ropes go through ropes? Well, first go to quantum and ask them, how do balls go through balls? And that's what you got to ask them. Okay? And until you get that question answered by them, don't question the rope. Okay? Otherwise, we all have to accept what quantum has already accepted. Things go through things. In Mother Nature's world, invisible.
No one is questioning that. No one really cares. The question is, how is this different? Where's the math? What are the predictions?
Intangible world. You just have to come to terms with that. Nobody has been able to come to terms with that in the last 10,000 years. And I'm asking you, if you're going to understand this universe, what is out there? What exists out there, right? Physics is the science of existence. Physics has to tell you what exists out there. A physicist has to tell you. The assumption you have to make is first, there are objects that you cannot see or touch, and these objects do go through each other.
Yeah, so, I mean, again, on the one hand, while I appreciate the creativity, on the other hand, just trying to go through the archive. Yeah, so it looks like the archive is just a written form of this. So it's 169 pages, which, sounds impressive, but it can go by really quickly, especially if you fill it with big pictures and big fonts. And yeah, I don't really see any... Yeah, it's not really compelling to me. So, the way to think of it is that it feels like a chef that, like, I feel like I'm a chef, and, I've gone through my training. I trained under, a rigorous chef. I did the hard work. I learned how to cut. I learned how to cook. I learned, all of these tricks and expertise and how to cook. let's say I learned from the French how to cook, in a French kitchen, and someone comes and says, hey, this is all garbage, it's useless, all you need is boiled potatoes. And it's just like, hey, I appreciate your creativity, but if you want to play the cooking game, you need to understand that what we've been doing has been done for a reason. The reason why we chop or we prep, why we marinate, so it sort of feels a bit like that, where it's sort of like, hey, everything is boiled potatoes. Let's put boiled potatoes in everything, and it's just sort of like I don't know what to discuss. So it has that sort of feeling of like, I appreciate the creativity. Everyone can cook. I'm sure you can make a great boiled potato. Stuff like that. But I cook a handful of dishes, and I work super hard at just cooking those dishes well, and that's all I can cook. And every now and then I can cook something good, but I have a lot of respect for professional chefs, and if I was to go and share my recipes, I would, just be humble about it, or just say that, if I really wanted to get into the chef's game, I would cook them a recipe and give it to them and say, here it is, please try it out, taste it, right? And then see what their reactions are. Go to the different chefs, and then go to the population as well and be like, what do you guys think? Because it's a different game. What the food that people like versus the chef's palate, it's kind of different. And so the same way, it's like the proof of the pudding is in the eating, right? So over here, it's sort of like he's talking about he makes the best boiled potatoes, but can I taste it? Can you cook it for us and give us a sample? And that's sort of what the mathematics of physics is about, is the actual cooking and serving, and and the actual tasting of it is the experimentation. So you can cook it, but the cooking is pointless without tasting, without having people taste it and give feedback. And that's what an experiment is that you need to cook it, but then you need to give it to people to taste. And that's sort of the feedback over here, is that he's talked about like a half theory about a boiled potato, but he hasn't talked about how to cook it, and he hasn't even cooked it, let alone given us something to taste. So I hope the analogy works. I hope I hope it's not too much of a strained metaphor, but that's kind of the best I can do right now.